Okay, let's get started. Okay, last lecture we looked at histograms. It was kind of interesting in that we looked at something that you're very familiar with as a picture of the density, and consequently as an estimate of the density. So we could actually look at statistical properties of the histogram if we imagine repeated sampling from the same distribution that generated the data we have in hand. In doing that, we could actually calculate expectations and variances, etc., and see what the characteristics are, the stochastic properties are of the histogram. And being a particular realization from some generative process, we could imagine having many of these and averaging them. And so the simple average we looked at was the average shifted histogram. So we took every interval and divided up into m equal pieces and used those as the breaks for different histograms, right? So just shifting over a small amount, h over m. And then we took the average height at any x, we took the average height of all of the m histograms. Okay, everybody remember that? So that's, any questions on that? Okay, the other interesting thing where we ended last day is that this can actually be written for x, this is for x in any particular bin, here the kth bin. This looks like, looking at the counts, the VKs, these are the counts in all the little tiny bins. And if we're interested in the kth bin here, these are the weights given to the counts in bins so far away, and only m minus 1 or on either side of the bin that we're looking at, right? So if you look at this function, this for m equals 5, it has this nice step function, so you get highest weight for the bin you're interested in, and then you give second highest to the counts next to it, and so on. It gradually goes down, as many steps as determined by the value of m, right? As m minus 1 steps on either side. And if you increase m, so here are 10, m's 10 instead of 5, you see you've just got many, many more steps so that the bins are tinier and tinier, and it's still giving that weight to the count of however many observations fall in that bin. And by the time we're up to 100, the bin itself is quite skinny. Each little bin is very skinny, so I've divided whatever bin width you had, I divided up into 100 pieces, equal pieces. And I'm using the counts in each one of those little tiny bins. And the weights that I have are going to be roughly dropping down like this triangle. So you can see that I've got this function here is dropping off. It's centered at where you're most interested in estimating the density, and then weighting things falling off linearly on either side. How far they go out depends on h, right? So I can think of that more as what I'm looking at is a weighted sum of these counts. In all of the bins, I'm looking at for the x value in any x value in that kth bin, I'm looking at a weighted function of the counts of observations in that bin and in neighboring bins. And that weight function is going to be a function of I, and it's going to be the granularity of the fineness of it's going to be determined by m. So m's kind of a parameter. Okay? Questions? All right, so that's what I want to look at. So a lot of this lecture, I'm just going to show you really hairy notation, then I'm going to simplify it, hide a lot of the details by introducing a little more notation, just to suppress the details so you can focus on what matters. So I want you to think about our estimate now for any x in the kth bin looks like this. It's just some sum over the counts in nearby bins, some weighted sum. And these are non-negative weights that sum to m, and that's just so that we actually get a density. And so I can think about, well, what's the behavior of this now under repeated sampling if I were going to get, another data set generated from the same distribution, etc. And the only thing that's determining changing values from sample to sample, if I keep the bins in the same places, is this count, vk plus I. right? So the counts of how many fall in that bin, it's going to be different for every sample. So that's the random variate, capital VK. So I'm just going to switch from lowercase to uppercase to indicate that's the random variate. And that means if I'm interested in the stochastic properties of this estimator, I'm going to be looking at the distribution here, right? VK plus I. And we know what that is. That's all going to be multinomial, etc. So I want to look at the stochastic properties of this quantity. So you can imagine doing that. And you could do that exactly as we did last time. The expectation of this is really easy. The variance, unfortunately, is no fun. Right? It just gets kind of ugly. But you could do this just using the sort of introductory statistics and probability course that you've taken. So we're going to try to make that look a little simpler. So that was for a particular, X had to be in a particular bin BK. And I'd really like this to be a density estimate that just is for anywhere on the real line. And so what I'm going to do is introduce the indicator function. And notation here is that if the argument X is in the set S, which is subscript, it's 1, otherwise it's 0. Okay? And that means I can now take our estimate here, which is the density estimate for any X in BK, and just put an infinite sum over here over all of the intervals, because this indicator function now will just pick off the one interval that matters, the kth one, for wherever X appears. Okay? So that's sort of trivial. All I've done is I've just inserted this, so now I can say this is true for all X in the real line. That's my estimated density. Okay? All right, so the next thing I'd like to get rid of this sum here. This sum is a funny sum. It's, the J has to be less than absolute value than M, so from 1 minus M to M minus 1. So let's make that an infinite sum from minus infinity to infinity, and again have an indicator function just do the work here. So if J is in this open interval, minus M to M, it gets 1, otherwise it's 0, and so these are identical. All right? The last thing is I really don't like these counts. I want to get to the X's. The X's are my actual measurements. So how am I going to do that? Well, I know the count can be found by an indicator function. If xi is in the interval b sub k plus j, then that's a 1, and it's 0 otherwise. So this sum over all of the x's is just counting how many are in there. So that's what it is. Okay? So now, my density estimate looks like this. So just putting all of those pieces together, it's a couple of infinite sums, double infinite sums, and a finite sum here. And x appears here on the left. That's the value I'm interested in evaluating the density at. And all the data points appear here in the xi's. Okay? So our density estimate looks like that. Everybody with me? Okay, so if you look at that, you can already see, as ugly as it is, some interpretability. So the value of x is going to tell you which bin is of interest, right? J is going to tell you how far from x these xi's are going to be. How far from x can the xi's be that will contribute to the estimate? Measured in bin numbers. And this weight here, it has an adjustable m that again tells you how fine this is, and gives you the weight for each xi in the bins. And finally, that h, that original bin width, is telling you how far away you're actually going to look for contributions to the particular x you're interested in. Okay? So you can see that happening here, although it's kind of complicated. Now, what I'd like to do is I really don't like these sums that involve infinity. So if I just rearrange these sums, just the order of summation, and pull this finite one out, and just take the 1 over n, throw the h in the middle here, I've got something that looks like an average. 1 over n summation I equals 1 to n of, well, this mess. Right? All I've done is move this around. So if I think about it, that says all that matters in here really, is this weight function and the x value that you're interested in evaluating it at appearing there, and the data that you had to start with. So let's call that 1 over n summation I equals 1 to n kh, the bin width, x and xi. So just some function. Okay? So again, ugly mess, and we're going to make that simple by just saying that's all that really matters. And so we know for the average shifted histograms that this function gives large values, gives large weight to those values of xi that are close to the value x that you're interested in, and small values for x's of the data points that are far away from the value you're interested in. Okay? Eventually actually to 0. So does that make sense? We're just going to look at this function now. And what's interesting about this function? Well, now I can think about the estimator that goes along with this. It's just this average of these k functions. In repeated sampling, the things that's going to change is this sample, the xi's. So that's my random variable, the capital Xi. Okay? The xi's are independent and identically distributed from the same density, right, which is how we're imagining the data are generated. They're coming IID from some density. I don't know what the density is, but they're coming from some density. Then that means we can actually take expectations and variance of this thing fairly straightforwardly. In particular, the expected value of this sum is just going to be equal to, well, that's a constant, right? This is a sum, so it's going to be the 1 over n times the expected value of the sum. Sorry, the sum of the expected values. And all of those guys come from the same distribution, so they have the same expected value. Right? I'm applying the same transformation to the xi. So just like anything else, all I have to look at is the expected value of this thing general for some x coming from that distribution. Make sense? And even better, I can use the variance formula, right? I know the variance of an average, right? The variance of I'm going to have 1 over n squared times the variance of that sum. The variance of a sum is sum of the variances plus sum of twice the covariances, etc. But what happens to the covariances here? They're all 0 because these things are independent. So this is just going to be the sum of the variances there. And so all I need is the variance of one of those. So it's 1 over, it's a, sigma squared over n. It's the variance over n because we're looking at the variance of an average. Okay? Make sense? Okay, and it all falls from the fact that the xi's are independent, and so the k of the xi's are also independent. So now I've taken this thing, not saying much about what k is. We know how ugly it is for the average shifted histogram, and saying I know how to calculate the mean and variance of these two pieces, provided, and all I have to do is calculate the individual pieces. So the expected value of the estimator is the expected value of this 1k function. So the question is, what should k be? Like that works for any k. It didn't have to be the average shifted histogram k. So to simplify, what's often done is we recast this and think about functions that are just location scale functions. So 1 over h. So this k function looks like 1 over h, some function k of the single argument x minus the data point xi over h. So you can think of it as location scale. The x is located at the xi with a scaling h, or alternatively the xi is located has a location x with scale h. I mean, x and xi are pretty symmetric in this thing. So I can think about this function now as a, what might be interesting is just think of that difference, that absolute difference. What's the scale distance away from x that xi might be to decide what weight xi should get? Okay, to decide what value it should get. This is called the kernel function. Okay, and so our kernel our density estimate looks like this, just this average of these kernel functions. Any questions? H here is sometimes called the bandwidth rather than the scaling, for reasons which will become apparent. Means I can get the expectation. So this looks pretty ugly, but let's look at what this is. So the expectation of, I only need the expectation of one of these, right? So the expectation of this quantity is going to be the integral of the thing I'm taking the expected value of with respect to the real, honest-to-God density, whatever it is. Don't know what it is, but whatever it is, that's the expectation, right? I can do a change of variables here from t to w. So t equals x minus hw, this change of variable. So now this thing is just I'm looking at k as a function of some variable w, right? And if I have this, when I look at this piece here, I think, well, that would be nice if the w's weren't so mixed up in with the x's. So what I could do is just do a Taylor series expansion. So you remember Taylor's theorem. So this is going to be f of x plus minus hw times f prime of x plus 1/2 minus hw quantity squared times f double prime of x, etc. Right? That's just the amount that I'm changing it by, plus minus hw. So Taylor's theorem, we just follow our nose through that, and then I'm just gathering the terms. The integral only has w, so anything that doesn't have w can get pulled outside of the w. So automatically I've got that this expectation, whatever the little f is, looks like this quantity, this infinite series. Right? Everybody with me? Yeah? Okay. So now I've got the bias. The bias is this infinite series that I have up here minus the real f of x that I'm estimating. So have a look at that equation and say I'd like that bias to be small. And I get to pick capital K. What characteristics would you like capital K to have? While you're thinking about that, also point out that the h, right, that's kind of like our bin width. And we saw we were going to make that get really smaller and smaller, right? So it's typically a small quantity, the h. So we imagine that high order terms in h are relatively small than terms that have no h. So if h is something less than 1, h squared is much less than 1, etc., etc. Any thoughts about what characteristics you would like capital K to have to make this thing small? But let's look at the term that doesn't have h. The term that doesn't have h is just this quantity here minus f of x. Could you make that 0? Yeah, you could make that 0. How? If this piece, if that piece integrated to 1. Right? So you say, well, if I required k of w to integrate to 1, that first piece is 0, so that's pretty good. that means that the bias is really only of order h, right, which is hopefully small. Can I make that bias of order h squared? Well, to do that, I'd have to make this term disappear. To make this term disappear, the only thing I've got in control is the choice of k. So I'd like that to go away. So I'd like that to be 0. So if I made that 0, that was also a requirement, then the bias would be of order h squared. Right? So if I required the integral of k of w integrates to 1, and the integral of w k of w is 0. Do you know of any functions off the top of your head that have that behavior? First of all, what functions integrate? Whoops, don't. Why are you bothering me? What functions do you know that integrate to 1? Sorry? Density functions. So density functions will work here. They integrate to 1. Suppose that was a density function, and we want that to be 0. What does that say about the density function? Has expectation 0. So if we have a density function that has mean 0, we know the bias is going to be of order h squared. So if we use a density function instead of that. So remember the density functions, remember the ash, we had a triangular sort of shape function. So here we're going to look at any density function would do with those characteristics. Similarly, I can calculate the variance in the same way. And the variance, I'm going to break in, this is the definition of the variance. And you know that variance can be the expected value of x squared minus the square of the expected value of x. And why do we do that? Well, because we already have that. Right? So the variance of our kernel function here is going to be, looks ugly, but it's the expected value of this square minus the square of the expected value, and we already have the second one. We just have to square it. Okay? So far, so good? So the expectation of the square is just this quantity here, right? So the expectation of that you're squaring the thing, that's the density that you're doing, so that's the definition, the expectation of the square. And do the change of variable that we did before, right? And this is approximately equal to 1 over h f of x times the integral of the square of the k function, of the kernel function. And you can prove that yourself. It's again another Taylor's theorem step. Okay? So you can get that as well, which means I can actually get the variance. And so the variance is just going to be this, the expected value of x squared, which we just got on the last slide, minus the square of the expected value, this thing here. Much of which disappears if we chose k so that integrated to 1 and that integrated to 0. Okay? So you actually have formulas for whatever the k is, at least approximate formulas. Any questions? Everybody follow that? There's less there than meets the eye. It's just a lot of just very simple steps. Just a lot of notation, even though we're only working with k's. Now imagine if we had all those indicator function stuff in there, it would be a disaster. So this suggests some things. If we made these constraints, right, so that integrated to 1, this has got an extra letter there. If that was 0, and if this last part was finite, that was the w squared term, you might call that sigma squared of k, right? Then we can express the bias is an order, the dominant term is order h squared, and the variance here is, again, 1 over nh minus s, and the remainder is of h squared over 2. Okay? So you've got that provided that happens. And a kernel that satisfies these things, we're just going to call it a simplified kernel. So if we wanted to get a little more involved, we could think about, well, how are you going to choose h? Right? Or how are you going to choose the kernel? Well, those are some constraints on the kernel, but I could think about for any kernel how I might choose h, and I may be interested in minimizing the average mean squared error over all of the x values, for example. Choose that and optimize things to get the best h, let's say. Okay? We're not going to do that, but you can imagine that happening. So, one choice that's very familiar would be a Gaussian distribution for a kernel. So you know that a Gaussian distribution is symmetric around its mean mu and has standard deviation sigma, which is the scaling factor. And if I call the scaling factor h, as I had before, the bandwidth, and I'm going to center the x around the data point, or alternatively, think of the xi being centered around x. It's completely symmetric, right? That will work as a kernel function. That'll be a simplified kernel. And how might you implement that in R? Well, that's straightforward in R. So I need a function that's going to take the x value that I'm interested in calculating the value at, the data that I'm trying to determine the weight for, and the bandwidth parameter h, right, the scale. And I do that by just getting the density for at xi for that mean x and that standard deviation. I could have also calculated it the other way around, d-norm at x for mean equals xi. 6 of one, half dozen of the other, right? And I can write a kernel estimate as follows. So I need the x that I'm interested in evaluating it at. I need the data, all the xi's, the bandwidth, h, and then whatever kernel function you've given me. So one reason of writing this beforehand is that that's a kernel function that I can hand as the value of the argument k here. Right? R is a functional programming language. You can have functions as arguments, you can return functions as values, etc. Okay? So, that being the case, I need to know how big is the sample, how big is the data, that's the length of the xi's. I'm going to get a vector here just to fill up with the values of the estimates, and then for everything in this length of x, how many values you want to evaluate this at, I'm going to get an estimate at every one of those x's. And so for the ith x, what do I have to do? I have to evaluate the kernel function for that ith x value using all of the data in that bandwidth. I have to add them up and divide by n. Okay? So this does it for a bunch of x's and returns all of the estimated values. Make sense? Okay. So these two functions together allow me to construct a Gaussian kernel density estimate at any point x. So if I look at the geyser data, the duration times, and I'll say my estimated density is this kernel estimate at point 3, at x equals 3. So say I'm only interested in x equals 3, and I'm going to use h equals 0.75. And the kernel function will be the kernel function that we just defined. So what I'm going to plot here are the values first along the, just plot all the data points, the x's along the horizontal axis, and then I'm going to draw the kernel function for all the estimates. So a kernel estimate at the x values that I'm interested in. The range of x values are going from the minimum to the max and a little outside, 200 values. Draw those lines, and then place my estimated point, the particular one at 3, on the plot. Okay? Everybody get that? So that's going to look like this. So that simple function, just adding things up using a kernel that was a Gaussian density, says that if you're interested in x equals 3, that's what I would estimate the density to be. And at any other point, here's the smooth curve that is my density estimate. So it's way smoother than that average shifted histogram, right? That kernel is making it very, very smooth. And the data points are here along the bottom. And so you can see the more points here, which is why we have a higher mode and a lower mode on the left. Any questions? So just putting together those little building blocks. And you could use any other kernel that was simplified, preferably, and find out what the density estimate would look like. So what's going on? So to give you a sense of what's actually happening, I'm going to write this function called a demo kernel. It's going to take the data, h, a kernel function, the x that you're interested in, and then some other information that's not necessary. So I got to get all the kernel values, right? Getting the centered at x, get the weights, all the kernels here. And again, I'm going to plot the data along the bottom of the line, bottom of the axis, the horizontal axis. Draw the lines like I did before. Draw some points at the density estimate. But instead of just the kernel, I'm going to actually show you what the kernel value is for those points, okay, at the x of interest. So for example, if I'm interested in focusing on x equals 3, right, this spot here, the kernel density estimate is this dotted line. The value that I'm estimating at 3 is that dot there. In the weights, the contributions of each one of those observations to the value at that point, x equals 3, are given by this Gaussian distribution. So I get higher weights very near the value I'm interested in, and diminishing weights farther away. Now, of course, this is going off to plus infinity and minus infinity. This doesn't have 0 weight, but it's really close to it. So that you should think about that much like when we did the average shifted histogram, we ended up with a triangle, right, with the bins. It's just now, instead of this hard triangle, or actually pyramid, I could have a smooth function, then I'm allowing each guys to contribute more or less depending on how far away they are from the point of interest. Okay, so that's what the kernel density estimation is doing with the Gaussian kernel in this case. Okay, so that's with bandwidth 0.75. So if I look at over here at x equals 2, the kernel now is centered around that x that I'm interested in, and these are the weights, these are the contributions to this estimate, scaled so you can see them, that give us this value of the density estimate for x equals 2. And well, before we move on, so what you imagine is actually happening is as I move from left to right here, saying I want to evaluate the kernel density at each of these places, I'm actually moving this Gaussian kernel function along the axis from left to right, along the axis, and at wherever the mean is of that thing, I'm giving the density estimate to be that sum of that average of those kernel values. Okay, so just moving this sort of sliding along, and you can see that h is the bandwidth. H is really the standard deviation of the Gaussian in this case. And you know, the smaller that standard deviation is, the more the Gaussian is going to pile up. The larger is the more spread out it's going to be. So that's kind of the bandwidth. When it's really small, it's a small band of the data that you're actually giving serious weight to. When it's large, everybody's getting lots of weight. Okay. So we can see the effect of reducing the bandwidth. So this is at 3 here, where as it gets smaller, it's going to pile up. So that it's piling up exactly around. So we get lots of points giving into here because it's very dense, but it's just those points that are nearby. So again, back here, with the same thing, not very many points are contributing, and you get a very low density. Okay. So you don't actually have to do that. We don't have to build these kernel functions. They may ask you to do that on an assignment because they're built-in functions. There's been a lot of research on density estimation. So there are density functions built in R, and we're just going to use that density function when we want a density, unless we're exploring how are they built. So the default density function from R is just get the data and plot the density. And you see it just comes up like that. It'll tell you how many points were in the sample and what its bandwidth was, what its H was. Okay? That's the default. And there are lots and lots of arguments here to choose, and lots of arguments to the density function. And the default here uses a particular way of choosing the bandwidth called NRD0. And I describe it there for you. It's in the help thing. But we're going to use what's generally recommended as a superior choice of the bandwidth is this Sheether-Jones bandwidth. And I give you a URL there for you to look at. So we're going to, when we build densities here in this course, I want you to use that bandwidth. And what do I mean by that bandwidth? That's not a number. That's a method for deciding on what the bandwidth should be for this data. Okay. So there are lots and lots of choices for the kernel function as well. You can choose different kind of kernel functions than Gaussian. We're going to use just Gaussian kernels and occasionally bi-weight kernels, which are, again, simplified kernels, but a little more robust in that, unlike the Gaussian, which never actually hits the axis, so everybody gets some weight, these will actually go hard to 0. So after some point, there'll be no contribution. The argument that I would like you to think about is this other adjust. So adjust is the way of whatever the bandwidth comes out by this automatic method, you can make it twice the size. So that's the multiplier of the bandwidth. So that would double the bandwidth that comes from that density function, right? So if you can double the bandwidth, you can half the bandwidth, et cetera, and as you increase the bandwidth again, you double it, triple it, and so on, it's going to get smoother and smoother because everybody's contributing. In some sense, if the bandwidth is large enough, it's just going to be completely, you won't see any details in the data at all. So here's halving the bandwidth. So when the bandwidth is half, you can see it's a lot bumpier, a lot smoother, which is why we have methods that are trying to guess what the bandwidth is. And doubling it makes it much smoother. Okay, so very bumpy, much smoother. Any questions? Okay. So in our, like most functions, density is returning some kind of structure. And you can see what information is there. It's got the x and the y values. It's got the actual bandwidth being used. It's got the call, which is in this case the default with those arguments. And so you can query this for information should you need it, should you want to construct things. In particular, I can get the density. I can plot it. That'll plot the outline here. And if I want it filled in, I'll just do a polygon on the density, because the polygon's going to look up the x and y values and do the fill in. Okay? So that's how I get a nice, sort of solid looking density. So another idea I'd like to introduce is that this is an estimate, and we know mathematically we can get some sense of how variable this is. We've tried to make this bias essentially very, very small. So another way of doing this is by pretending that the sample itself is actually all the data that exists, and then you resample from it. So I take another sample without replacement of the same size from the original sample. Okay? And that'll give me new data set. How many people have seen that before? Nobody? How many people have seen bootstrapping before? A lot more people. That's all bootstrapping is. Right, so I'm going to take the sample and pretend that that's actually the population that I get this sample from. So what I'm going to do here is exactly what I just did a minute ago. I'm going to get the density, plot it, and draw a polygon with some plot color. What's different is I'm going to do that 100 times. Each time I'm going to get a sample of the data with replacement of the same size sample. Then I'm going to get the density for that sample. Then I'm going to plot just the density. I'm not going to plot the border. I'm going to plot the filled in part. And what I'm going to do is slightly different. I'm going to use the color that you give me. I'm going to make that transparent to be 1 over 100th. So I would need to pile 100 of these guys up for that to be solid. Okay? And if I do that and look at the plot, there's our density estimate. And so it still is kind of capturing what's going on in the data, but that very blurriness is trying to communicate some variation, some uncertainty. Okay? Which I think is a good thing. Like any other estimate, you're not taking this too seriously, that is the actual density. That's our bootstrap estimate showing the variation, which is communicated through that alpha blending, that blending of the transparencies. Okay? So you go back to your visual fractions when you're trying to communicate randomness, uncertainty. Here I'm trying to communicate some sort of randomness or uncertainty, the density estimate. Okay? Everybody understand what that picture's about? Okay. So let me tell you another graphics model. As I said before, throughout I'll be using primarily the base graphics in R. They're very simple, very straightforward to construct anything that we want. And if I wanted to really develop new graphics, I would be using the grid system. The system I'm talking about here is built on top of grid. And it's called ggplot2. And what this is GG is for the grammar of graphics. And this was an innovation by a fellow named Lee Wilkinson, who, based on his many years of building several systems, graphic systems, decided on a particular model, a pipeline model for constructing visualizations, for constructing statistical graphics. And very roughly speaking here, what I have is I have a plot, which I take the plot and I pipe it through into a coordinate system. I pipe it through some scales. I maybe look at some facet of it, and then I produce layer, and then another layer itself. And every layer consists of pieces, a chunk of data, a mapping, some statistical summaries perhaps, some geometry about that you want to present, and some position. And so this looks, I think, overly complicated, right? Especially at first, when you first encounter this, you have to really do this a fair bit to become accustomed to the grammar used in a regular way. Very handy for doing routine kind of data analyses. It allows you a lot of power, to very expressive, to split things up very quickly and see what's going on in the data. To build new graphics, as I said, I would prefer to be working with grid itself, which is what ggplot's based on. So I'll give you some sense of what this looks like. So in this case here, so the ggplot2 is the package. So I could say ggplot, the data equals geyser, the mapping is, and then AES is aesthetic. The aesthetic is that x equals duration. And to that plot I add a geometric object called the density, a geom underscore density, which has this color gray 50 and a fill color. And because it's density, some parameters here like that bandwidth that I'm passing off to the density function. Okay? So this ggplot returns a plot, and geom density adds a density view to that of the data that's contained in that plot. Okay? When I do that, that looks like this. So to make that more explicit, I can actually save that ggplot. Nothing happens. So I've just created it, and I've got this object called myPlot. Then by typing myPlot plus this geometry, geom density, I get this picture. So it's trying to do some clever things automatically, like giving you a grid background that makes it easy to look things up, but it's not really in the way. It's got the particular aesthetics that the author has decided on they like. But this thing adds something to myPlot and displays it. So this actually is the printed representation of that statement. MyPlot itself is not permanently changed because there was no assignment here. Okay, so nothing's happening by side effect there. So I could also do this with, I haven't made a new myPlot, the same old myPlot, and I just add the histogram, geom histogram, and I get this result. Okay. What's cool is I can add layers. So these are layers. So now I have my plot, add the layer of histogram. I want its fill to be white, right? And then add the density, fill gray, but I want it to be transparent. I want it to be 50% transparent. And that allows me to overlay that density estimate on top of the histogram. Okay? So you see the layering. I've got a plot, I've added this histogram, then I've added this layer. And you have to, when it's split over lines like this, you better end your line with that plus so R knows it's got another line coming. Okay? So what do you suppose would happen if I reverse that order? If I had my plot plus geom density plus geom histogram. Same thing? The histogram is going to be on top. Is the histogram transparent? No. So it's going to look like that. So the ordering of the layer matters, and you have to think about what you can see through, what you can't see through. So I mean, it's not unlike many sort of graphics systems that you've worked with where you get the layer stuff. So, you know, whether that's PowerPoint or Keynote or what have you. So if I want to build a quantile plot, since this isn't built in to ggplot, at least not to my knowledge, not built into ggplot2, I have to sort of construct it by hand. So now I've got to get a ggplot. This is my quantile plot. It's mapping. I'm going to have to tell it, I know it's the data is the geyser data, but I want to get the p points for that duration. And then I want to sort the duration, will be my y values. Now, to get a scatter plot, it's my quantile plot that I've set up, plus this is how I mentioned that there are points. The geometry I'm interested in is a point, geom point, which I'll make transparent. Its transparency only one quarter in color steel blue, and I add labels. Right? So that's the work I do to get that. So it's a very different model, and I've really gone over that very quickly. A lot of the choices I've got there, what is AES and what is mapping, all of the rest of that stuff. There are lots of introductory books that'll let you go through ggplot2. Again, for the most part, we won't be using it because I'm interested in constructing things. I'll just show you things from time to time using ggplot2. And where it's really handy for this course anyway will be in facets when we talk about higher dimensional data. Okay, till next day.